In this video, we're going to walk through how Scheme works, and we'll talk about some of the data types that exist in Scheme. So one quick definition before we start. A Scheme form is something that you ask Scheme to evaluate. Essentially, it's an expression. And we're going to be using Dr. Racket. Dr. Racket has two windows. The top window is an editor where you can type code, and the bottom is a REPL, REPL, which stands for Read, Evaluate, Print Loop, where you can work interactively with Scheme. We'll primarily use the editor just so that we can save what we're doing, but there's no reason if you weren't just trying to come up with some calculation, you could do it all in the REPL if you wanted. So the simplest forms would be what are called self-evaluating forms. Those are just things that evaluate to themselves. So an integer, a string, things like that. We can also have forms that include an operation, and we surround those with parentheses. So plus 1, 2 is how we would add 1 and 2 together. Since Scheme uses prefix notation, there's no limit to how many operands an operator can have. So this will add 1, 2, 3, and 4. And we can also have nested expressions. So we can say 1 minus 3 minus 2 plus negative 4, 5. And we can evaluate all of these together that are in our editor with the run command. And that evaluates everything in our editor. So there's a couple ways to do comments in Scheme. So comments start with a semicolon. We can also comment out an entire form with a hash semicolon. And what's nice about that is that also allows us to comment out a multi-line form like this. So that's helpful if you have a longer function that you're writing that doesn't actually work. You can comment it out just to avoid getting errors when you run your code. So the define procedure associates a name with a value. And you'll sometimes see this referred to as a variable, but it's not really a variable like in a language like C or Java because you can never change what this number is. Now when we run this, notice we don't get any output because all this does is associate that name to the number. But in our REPL, if we type my number, we get 10. And then we can use that name anywhere we want, and it will be evaluated to the number 10. But keep in mind, we can't redefine that. So you'll notice here it says you can't redefine a constant. I can also use define to associate a string to a name. And let's put some examples of using this. Just so we have some of those in our file that we'll save. And you can see that no errors here because that name is defined here. And one nice thing about Dr. Racket you'll see is when you mouse over a name, it'll actually refer to its definition. Now define is defined actually in the language. And so notice if I mouse over define, it'll tell me that that comes from Scheme. And that's really helpful for later on when we do more advanced procedures and so forth, when maybe the scope of some of the names may be confusing. You can use that mouse over technique to figure out where a certain name is defined. And Scheme will let you define pretty much anything as a name. So here is a name with a bunch of special characters and so forth. And so now if I add that to 10, it'll actually evaluate that to 5 and add 10, and you get the result 15. So for cleaning up your output, there's a nice form called newline that evaluates to just an empty line. You can see that here. Typically, though, you won't add that to a procedure. It's just something you may want to add to a file that has a lot of output to clean things up. So here, data types will evaluate to a string. And when we run this, notice we get nice output saying, hey, here are some data types, and let's go ahead and define those in our code. Here's a few examples of the different types of primitives you can use. So you can have integers, you can have real numbers, you can have strings, and let me line this up real quick. So here I have the multiplication operator, and that's a primitive. And if I run the code, you can see that that actually evaluates to the procedure defined with multiplication. We can have Booleans, and we can also have characters defined as so. So now let's talk about symbols and strings. So if I ask if hello is a symbol, and then I ask if world is a symbol, when I run this, you see that this is a string. It's not a symbol, but world is a symbol. And you may say, well, they look pretty close. One just starts with a single quote. The other is enclosed in double quotes. There's a few differences, and we'll discuss those as the semester moves on. But one thing to keep in mind right now is that if I have a symbol, symbols are unique. So there's only going to be one symbol anytime I have a symbol. If I use it in different places, those things are the same symbol. But if I have a string, it's possible for two strings to actually not be the same actual object. Similar to how in some languages you have string literals that would be unique and stored in static memory, and so every reference to one of those would be a reference to the same string. That's not necessarily the case. In Scheme, we can have multiple strings that have the same characters. They're the same string, but they're not the same object in memory, whereas symbols are going to always evaluate to the same entity. And let's copy and paste this code and check for a string now. And you can see in this case, now hello is a string and world is not a string. I can actually convert back and forth between the two using the symbol to string or string to symbol operators. So when I run this, you can see that I get the string hello and the symbol world. So now let's see what numbers are. And you can see that both of those evaluate to false. But this third one, the third one does evaluate to a symbol. Now, one thing you may ask then is, can I do something like this? Can I add plus 8 and 10? And notice it treats that as just an integer. So now let's talk about some numeric types. We talked about a few above, but let's see a few others. So we have integer types, we have binary types, octal types, hexadecimal types. Notice those start with a hash and then B, O, or X, depending on which of the binary, octal, or hexadecimal it is. Real numbers, we have fractions, and then we also have imaginary numbers. So if I run this, you can see that my fraction gets reduced. 7/3 becomes 2 1/3. The numeric types also have predicates as well, just like we have for symbol and string. So if we say integer 3, that's going to be true. You can see that that's true down here. So what if we ask if 3.0 is an integer? And an easier question, is 3.1 an integer? And here you can see 3.0 is an integer and 3.1 is not an integer. How about if we do this? Integer times 3, 1 divided by 3, and integer times 3 divided by 1, 3. So notice in the first case, we actually did a fraction. Here we did a division. And in both of those cases, it's true. So that might be a surprise to you, because if you did floating point arithmetic in a lot of languages, something like this wouldn't be 1, it would be 0.99 or something like that. There's a predicate for real numbers. I can ask if 3 is real, if 3.0 is real. I can ask if 2 plus I is real, and I can ask if 2 plus 0i is real. And when I run this, notice 3 is real, 3.0 is real, 2 plus I is not real, it's an imaginary number, but 2.0i is 2, and that's a real number, so that returns true. Scheme is actually really good with numbers and figuring out the types of numbers. You don't have some of the errors you'll see introduced by using real numbers in by using floating point numbers in other languages. There are some other number predicates that we can use. We can ask if 1 divided by 3 is rational. We can ask if 2 plus I is complex. And we'll ask if 2 plus 0i is complex. And while we're at it, let's ask if 2 is complex. And we'll even ask if 2 plus 0i is rational. So let's run this, and you can see that the answers are all true. All of these cases are true. We can be more general and ask if something is a number. We'll try a complex number there as well. And just some silly cases we'll try. We'll ask if the car of the list 8, 10, 5 is a number. We'll ask if the string 1 is a number. We'll ask if the symbol 2 is a number. And finally, we'll ask if the symbol 3 is a number. So when we run this, remember that was the symbol 3 is actually the number 3, whereas these two are both false. This one evaluates to true. You can see that here. And both of these are numbers as well. So one thing you want to make sure you avoid doing is thinking in terms of other languages, how they deal with numbers. It's definitely a lot different when it comes to Scheme. Okay, so now let's do some math. Again, remembering that Scheme uses prefix notation. So we have plus 10, 10 to add 10 together, times 10 and 10. We can also add 1 and 2, and we can times 3 and 4. So let's run this and see what we get, and we get the numbers we would expect. We can also subtract 1 and subtract negative 1. So this might be a little surprising. So this gives us negative 1, and this gives us positive 1. We can add multiple numbers together at once. And we can also multiply multiple numbers together at once. We can also subtract a bunch of numbers at once. Notice there we get negative 47 because this is 1 minus all of these numbers. So it's a negative, and there's a difference in the absolute value of 2 because we're subtracting 1 from the absolute value instead of adding it as we did in the first case. And how about if we divide 100 by 2 and 5? We get 10. So we can even do really long and drawn out arithmetic expressions like this. Also, one thing to notice is that it'll do matching for you on your parentheses. Take advantage of that. Right now, everything we've done is fairly simple, at least until we got to this one. But later on, we'll see some procedure definitions and so forth where you'll have a lot of closing parentheses. And so it's very useful to have that feature to make sure you get those things matched up. There's some mathematical functions like square root. Let's do the square root of negative 1 just to have some fun. And notice the square root of negative 1 is 0 plus 1i. And you can see the other values here. If I divide 17 by 3, you get 5 2/3, which is correct, but might not be what you want. So if I say 17 divided by 3.0, that'll give me a real number as my answer. Finally, there's a quotient and a remainder function. And so the quotient of 17 divided by 3 is 5, and the remainder is 2. And you can see that when we got the fraction, 5 2/3. One other quick thing. So here we have some ridiculously big numbers. And let me just let's not add letters. We add a couple more digits here just so it's a sufficiently big number. And when I run this, notice it computes the result. Scheme can handle very large numbers. So now let's work with some defined names just to show you how that works. So if I define x to be 10, y to be 20, I can say x and I can say y, and when we run this, you can see that x evaluates to 10, y evaluates to 20. Now if I define z to be 30, and then let's evaluate z, you'll see that now z defines as a procedure z. And this is sort of a shortcut to defining a procedure. This isn't a very interesting procedure though. It's a constant procedure, so z always returns 30. And we actually won't be defining procedures like this. We'll use lambdas just because doing it like this is syntactic sugar on what's really going on. It's always good to be explicit when you're learning a language and not rely on shortcuts. So I can add 2 to x, or I could also add x to 2. I can multiply x times y divided by 6. I can check to see if x is equal to 12 or if x is less than 12. So let's run this and see what we get. And all of these give us the result that we would expect. Now if I say equals 30 to z, it's not going to like that because z is a procedure. And notice here I get a contract violation error. It was expected a number and I was given a procedure. So if I wrap this in parentheses, it'll like it because that procedure z evaluates to 30. I can also do more complicated equality checking. Like I could say, is x equal to 15 plus negative 5? Or is x less than times y 3? And here we have a contract violation because that should be a negative 5, not just negative. And so you can see we get the results we would expect. This is equal, and x is, oops, I meant to make that less than, but this is greater than, and it still works. X is not greater than y times 30 because y, as you remember, is defined to be 20, so this evaluates to 60, which is certainly not less than x. So one last topic in this video that I want to talk about is equality checking. So to do this, I'm going to define a num to be 8. So first, let's look at equals. There we go. I think I fixed that. So we'll do equals first. And is 32 equal to 32? Is 32 equal to 4 times the num? And is 8 equal to the num? And if we run this, we can see, oh, another contract violation here. Oh, that shouldn't be equals. So when we run this, you can see that all of those are equal. Now, if I try to say equal, hello, and hello, you see I get a contract violation because it was expecting a number. So if we're going to compare other things, there's eq. And I can say eq like this. And now, yes, those are the same symbols. So what about strings? So those are equal as well. So let's try an even more difficult case. What about equal CSC and symbol to string CSC? And notice that's false. Now, those are both going to be the same string. This evaluates certainly to this string, but remember they're not the same instance of the string in that case. Here they are because there's 2 string literals, and so those do evaluate to the same. But you want to be careful using that to compare strings. And by careful, I mean you don't want to do that. So let's put equal in place of the equal sign here just to show, or just to see if that still works. And you can see here it does. A couple other things to check. We haven't talked about list yet, but we will. So is the list 1, 2, 3 equal to the list 1, 2, 3? And you might say, yes, they are. They may be equal, but they're not equal. So one more, if we say equal 8, and then let's do some arithmetic, plus 2, 3, 3. And we can see that that's true. And this will evaluate to true if we use num instead of 8 as well. Because again, num evaluates to 8. Finally, let's use equal. Let's just take all our examples above and convert eq to equal. And when I run this, notice that all of these evaluate to true. So a general rule of thumb is when you're checking equality, the more characters you have in your operator, the deeper the equivalency check goes. So this is not just checking that the things are the same object, it actually goes in and checks to see that do the objects have the same value. So it's similar to the difference in Java, where if you use the double equal operator, that checks to see if two references are referring to the same object, whereas if you use the equals function, that'll do a deeper equality check to say, do these two objects have the same value? So that's a quick introduction to some of the data types and scheme and some of the predicates that we can use to work with and check the type of those literals.